This video clip reviews some of the material we discussed in the mass wasting learning module. A lot of the mass wasting learning module had to do with slope stability or slope stability analysis. Slope stability analyses try to answer the question, is this slope safe or is it likely to undergo some type of mass wasting? Like, is this slope likely to have another rock slide like the one that you can see occurred here in the past? Trying to answer that question involves assessing the driving and resisting forces acting on the hill slope materials. So here's a little diagram where we've got some material sitting on a hill slope. Maybe it's unconsolidated material that's on top of solid bedrock, so the dark brown wedge here represents solid bedrock farther below the slope surface. And we're trying to figure out, is this material here in the lighter brown color likely to move, or is it going to stay in place? So that involves looking at the driving force that's acting to try to pull that material down slope, which is represented by this down slope pointing arrow, labeled F sub D for the driving force. And also trying to assess how big this resisting force is. So let's review what the driving force behind mass wasting is. It's basically related to the weight of the slope materials. So it depends on the weight, or you could say the mass of the materials on the slope, either way. But it also depends on how steep the slope is. So, you know, what this slope angle in here is. Right? So we could say it also depends on the slope angle, how steep the slope is. The steeper the slope is, the greater the downslope or driving force. And the resisting force behind mass wasting is simply the strength of the slope materials. So anything that increases the driving force would make mass wasting more likely to occur. For example, if as a result of construction activities, build a house on here, this is kind of the size of a dog house more than a human house, but the idea is that if we add more material to the slope, and that adds weight to the slope, part of that weight is going to act in the downslope direction, and that would increase the driving force if we increase the weight of the material on the slope. The other thing that could change possibly is the slope angle. Maybe as a result of human activities, if we remove material from the base of the slope, that would make the overall slope angle greater, and increasing the slope angle would increase the likelihood of mass wasting occurring on the slope. We said the resisting force, the strength of the slope materials, that depends on the properties of the slope materials, like the cohesion of the materials. And in unconsolidated materials, the internal friction within those materials is a big factor, especially for materials like sand or gravel that don't have any cohesion to them. Now, if we wanted to measure these things, we could take samples of the slope materials and do strength tests on them in the laboratory and assess the strength of the materials on the slope to, get some numbers on the magnitude of the driving force behind mass wasting, or how big the driving force is. We'd have to make an estimate of how much this material on the slope weighs, and we could more easily measure the slope angle, and depending on the geometry of the situation, there are formulas that we can use that might be relatively simple or more complicated to compute an estimate of the driving force behind mass wasting as a function of the weight of the slope materials and the slope angle. The learning module also talked about some of the things that could affect the strength of slope materials. And one of the most important things is water. Remember that saturating the slope materials with water weakens them. And the most common trigger of mass wasting is something like heavy rain or a lot of snow melt water that saturates the slope materials and weakens them to the point that they begin to move. Another thing that can affect the strength of the slope materials is earthquake shaking. And this huge area, this mountainside here, came crashing down and dammed up the Madison River in southern Montana west of Yellowstone National Park as a result of an earthquake in 1959 that triggered this huge rock slide. Right? So earthquake shaking can also be a trigger of mass wasting. Another factor that can affect the strength of slope materials is that some materials have inherent planes of weakness in them. For example, sedimentary rocks, like you can maybe make out up here on the mountainside, these are sedimentary rock layers. The bedding planes or the surfaces between the rock layers are weaker than the rock between those layers. So when we have a slope like this one where the bedding planes or the layering in the rock is parallel to the slope itself, that's a more dangerous condition because we have those planes of weakness oriented parallel to the slope, and the downslope pull of gravity can pull on that weakest part of the rock to try to make it move. Another factor we discussed in the learning module was vegetation. Usually the vegetation on the slope surface has a stabilizing effect and helps hold the material in place. In less common cases, sometimes the vegetation is very heavy and adds too much weight to the slope and makes mass wasting more likely, but usually it's a stabilizing factor and helps to prevent mass wasting. So returning to our slope stability diagram here, we can write a ratio that's known as the safety factor. Let's abbreviate it SF, safety factor, that compares the resisting force to the driving force. Of course, we'd like to have our slope materials be very strong, have this resisting force be large relative to the driving forces trying to pull those materials down slope. So we'd like to have the safety factor be greater than 1. And usually we'd like to see it be considerably greater than 1. So let's say if the safety factor is greater than 1.3. we could consider the slope to be relatively safe and unlikely to undergo mass wasting. It's when the safety factor gets close to 1 that there can be problems and there's a concern, right? Because if the resisting force is only a little bit greater than the driving force, the safety factor is maybe 1.1, 1.2, something like that, then maybe if conditions on the slope change, mass wasting would occur. And then if the safety factor is less than 1, it means the materials are weak relative to the downslope driving force, and that's an unsafe slope. We would not want to build our vacation home in the mountains on the slope that has a safety factor less than 1. So I hope this makes it a little more clear what the driving and resisting forces are in mass wasting. I gave some examples of how they can change under different conditions, and then how we can compute a safety factor to assess whether the slope is relatively safe or whether it's likely to undergo mass wasting. Let me know if you have questions.